Yeah, sure, no problem.
Okay.
Okay, can you see my screen?
Yes.
Great. Then I guess I can start now. So, hi everyone. My name is Fei Wang. I'm a PhD candidate at University of Southern California. So today I'll present our recent work on robust and context-faithful language understanding with large language models. So large language models are not extensively employed in real-world scenarios. I believe many of us have used them to draft documents or write code. Here are some statistics about large language models. So the most popular language model service like ChatGPT, they may have millions of users and billions of visits per month. And language models also have significant influence in our daily work. Around 80% of the US workforce could have at least 10% of their work tasks affected by language models, according to OpenAI report. And also billions of dollars have been invested to accelerate language model development. So all of these facts indicate that language models have significant social impact. However, are these models entirely reliable? You know that these facts also indicate that any issue or bug in these models may have the potential to affect millions of people. Consequently, the accountability of them is becoming increasingly important. So in this talk, I'll focus on the following research question: how to make large language models more accountable. The first accountability issue I'd like to highlight is contextual faithfulness. So assume that we collect data to pre-train language models by September 2021. There could be a piece of information indicating Twitter CEO is Jack Dorsey. And after pre-training, the language model will memorize this information in its parameters. Then we'll deploy the language model to provide services. However, let's say 1 year later, the Twitter CEO becomes Elon Musk. It's no longer Jack Dorsey. So if we provide a news article about this change as context and ask the language model, who is the Twitter CEO, the model may still tell us it's Jack Dorsey, ignoring the information we provided. So this example shows that language models may overly rely on its own memory to provide unfaithful responses and spread misinformation. So since knowledge is always changing, it's impractical to update the model parameters whenever some information change. So that's why context faithfulness is crucial to language models. Here are some more critical examples highlighting the importance of contextual faithfulness. Assume that we are asking the model some medical or financial questions with some recent news articles as context. We know that the language model may already memorize some information about these vaccines or banks during pre-training. Things may change, and there could be some updated information that the model do not have in its parameters, and that may lead to wrong medical or financial answers. So although language models could be more cautious, it will negatively influence the model's helpfulness. So we do not need a model that always responds with, I don't know. The second important accountability issue is robustness against various prediction shortcuts. So here's an example of paraphrase identification. We may have such an instance in the training corpus: Alice married Bob and Bob married Alice. So they are paraphrases. The model trained within this instance may learn a spurious rule that if two sentences have exactly the same words, then they are paraphrases. However, during inference, we may face an instance that the rule is not applicable. AlphaGo defeated human and human defeated AlphaGo. So of course, these two sentences are not paraphrases. So this toy example shows that large language models may make predictions based on unreliable shortcuts. And previous works have found that language models could capture various unreliable shortcuts, such as lexical bias, entity bias, and also position bias. So these biases hinders the accountability of large language models. Here are more examples from medical or legal domain. So language models may also learn shortcuts in this data size, which may lead to wrong medical or legal decisions. So we can see that relying on these shortcuts could be pretty harmful. So in this talk, I'll introduce our recent work on enhancing the faithfulness and robustness of large language models. So let's start from the first section, how to enhance their faithfulness. So why do we need context-faithful large language models? As I introduced in previous slides, large language models acquire a lot of word knowledge from the pre-training corpus, and the knowledge will be memorized in the model parameters, known as a parametric knowledge. The problem is that this kind of parametric knowledge is not always reliable. First, parametric knowledge could be outdated. In real-world usage, knowledge updating is essential. Second, there could be missing knowledge during pre-training. We may not be able to collect all the human-generated text to create a pre-training corpus. And even if we have such an ideal pre-training corpus, the model may not be able to memorize all the information in the corpus. And third, there are always private knowledge, such as medical records or other sensitive personal information that we do not want the model to memorize because language models are not secure storage. However, the model needs this knowledge during inference to solve some NLP tasks. So a straightforward way is to provide this updated, missing, or private knowledge in the prompt as contextual information so that a context-faithful model can give us precise responses. This is essential to address various NLP tasks such as summarization, information extraction, and also question answering. The bad news is that large language models are not born to be context-faithful. As demonstrated by the TutorCO example, there could be conflicts between parametric knowledge acquired from the pre-training corpus and the context knowledge provided by the users. So language models need to address the conflict to give us a faithful response. Unfortunately, they often overly rely on their own memory and ignore the context. Another problem is that even if there is no conflicts between these two kinds of knowledge, the model may still ignore the context. In this example, Jeff Bezos went to Amazon neutral nodes. The relation between Jeff Bezos and Amazon in this sentence is visitor of rather than founder of. However, the entity mentions in this sentence may trigger the model to make trivial guesses and respond with founder of instead. So to address this problem and enhance model faithfulness, we first analyze the problem from a causal view. We view the problem as a following structured causal model. In this SCM, X is a raw context, E is the entity, and Y is a prediction. Our goal is to predict the Y based on the context X. However, entities E contributes to X and may also trigger trivial guesses of Y. That is to say, E becomes a confounder. So to mitigate the influence of a confounder, we can apply backdoor adjustment. So instead of computing the prediction based on the raw context and the original entities, we can perturb the context with other entities and compute the weighted average prediction. Considering that large language models typically follow a sequential structure by stacking neural layers, mitigating entity bias in one layer will also mitigate the entity bias in subsequent layers. So in our work, we propose to mitigate the entity bias in the input layer, which is easier to implement, ensures less error propagation and computational cost, and can also be applied to both white box and black box language models. In the next few slides, I'll show how to apply this causal intervention to both kinds of language models. First, let's see how to perform causal intervention on white box language models. For white box language models, their training precise and model weights, including embeddings, are accessible. Assume that this large blue circle is embedding space, and we have an original entity, for example, Jeff Bezos, shown as a star in this embedding space. We can find several neighboring entities surrounding it, such as Bill Gates or Steve Jobs. Then we can create a convex hull by connecting these neighboring entities. So the embeddings within this convex hull share the same predictive information. So during inference, we can use the center of the convex hull to replace the original entity. And during training, we randomly sample embeddings within this convex hull to mitigate entity bias while increasing data diversity. Intuitively, embeddings close to the original entity consist of both predictive and biasing information. And if we move away from the original entity, embeddings can become more general. The information it possesses are less biasing, but also less predictive. So the center of the convex hull strikes a balance between these two kinds of information. To evaluate contextual faithfulness, we create a counterfactual evaluation set. For each instance in the original evaluation site, such as Jeff Bezos is the founder of Amazon, we create a counterfactual counterpart by substituting the context, like Jeff Bezos paid a visit to Amazon. So as a result, the answers to these two sentences with the same entity pairs are different. They have different relations. Here are the results of the original model on the in-domain data set and the out-of-domain data set. So we can see that there is a significant performance drop from 71 to 62 when we substitute the context. And our method can significantly improve the model performance on the out-of-domain data. These are some
So just to confirm, this is out of distribution, right? Not out of domain.
Yeah.
Yeah, because you just said out of domain. Yeah, never mind.
Yeah, sorry. Out of distribution, yeah, the context distribution is different. Yeah, so yeah, these are some baseline results. And I'd like to mention that these methods are could be seen as a special case of our following our causal intervention framework. So you may have noticed that there is an important hyperparameter in our method, the number of neighboring entities to create the convex hull. So this figure shows the model performance with different numbers of neighboring entities. We can see that as the number increase, the out-of-distribution performance first increase, then decrease. So this is because when the number is too small, the center of convex hull is close to the original entity and thus contains more biasing information. While the number is too large, the center of the convex hull becomes too general and loses essential predictive information. As a toy example, if the original entity is Los Angeles, when we increase the number of K, it first becomes a fine-grained representation city, then a coarse-grained entity type location, and finally, a general representation of entities. So there is a balanced point decided by the task properties which we can search on the development site. Yeah, before we move on to the black box intervention, is there any questions or comments? Okay, I'll move on. So when we extend our methods to black box language models, we have another bad news. We are not able to access model weights, gradients, or logics because the service provider want to protect their intellectual property. And as a user, we can only interact with the model by sending prompts and receiving responses. Therefore, we have the following research question. Can we perform causal intervention on prompts to enhance contextual faithfulness? The answer is yes. Given the prompt that Jeff Bezos went to Amazon Natural North, we can perform the following interventions on the prompt. So we first replace the entities with some neutral placeholders like subject entity or object entity. Then we can define these placeholders with the original entity and similar entities. For example, subject entity can be any of Bill Gates, Steve Jobs, and Jeff Bezos. So these entities in the questions will also be replaced with some neutral placeholders. So all of these parts, the entity replace the context, entity replace the question, along with the placeholder definition, it together serves as a debiased prompt. Next, let me show the intuition behind this causal intervention. So take this definition of subject entity as an example. The original entity, Jeff Bezos, contains information like founder of Amazon, founder of Blue Origin, and the entity type is person or businessman. So some of the information is biasing, while some is predictive for the relation extraction task. By defining the placeholder with similar entities, we can mitigate biasing information and get a representation of common features shared by this set of entities, which is the entity type person. For this black box setting, we evaluate our method on GPT 3.5. Similar to the white box setting, we create counterfactual evaluation set by substituting entities. Here is an example of question answering. We replace Bill Gates with Steve Jobs. So when asking who founded Microsoft, the faithful language model should respond with the replaced answer rather than the original answer. So here's the model performance on this machine reading comprehension data set. The original model got an exact match accuracy of about 27. If we query the model with the context and emphasize that the answer should be based on the context, the performance is better. It becomes about 37. And if we present the context as one's opinion and asking about the person's opinion, the performance is even better. And with our causal intervention, the accuracy becomes 51. So we have similar observations on the relation extraction task. Okay, so here are the takeaways from the first section. First, contextual faithfulness is essential for solving various NLP tasks like question answering and information extraction. Second, language models are not born to be context faithful. They always overly rely on their own memories in the parameters. And finally, causal intervention is an effective approach to enhance language model faithfulness. So we have shown that our causal intervention can be applied to both white box and black box language models. Yeah. Any questions about this section?
Okay, I think this kind of using entity as a shortcut can be seen as a way of fast thinking by the language model, right? So of course I'm familiar with your solution here, but the other way around is I'm actually thinking, can rationalization help us here? What do you think?
Oh, that's a good question. Yeah, I think this work we focus on the causal analysis. So adding rationales could make the causal graph more complicated.
Right.
But I believe that if we can extend our causal framework to more complicated cases, it will be more like practical, right? And I believe, yeah, I do think that rationale will help. Yeah, I think they can also serve they can also be seen as a kind of causal intervention because we are trying to add more causal factors in the input, right? Yeah. Yeah, thank you for the question. Okay, so the next part is about enhancing language model robustness. So language models often capture unreliable prediction shortcuts during training. Prior works have discovered various biases in language models, such as lexical overlap bias, hypothesis-only bias, lexical bias, entity bias, and also position bias. I have mentioned most of these biases before. The only one left is hypothesis-only bias. So in natural language inference tasks, the model is given a premise and a hypothesis, asking whether the premise entails the hypothesis. So researchers found that in some fine-tuned models, even if we only provide the hypothesis, the model can still give us a correct answer. That is to say, there is a hypothesis-only bias in the data set. The premise didn't work as expected. So although prior works have identified and resolved many biases, we are still far away from robust language models. The first problem is that these works discover and address each bias independently. There could always be more unintended biases that haven't been discovered yet. And we know that most of these biases are defined on the textual features. Since we are using neural models, there could even be biases on high-dimensional features, but we do not know. The second problem is that even if we have discovered all the biases in language models, designing customized method for each of them is inefficient. And finally, even if we do have techniques to resolve each bias independently, combining them into one model is still intractable. Therefore, we need a general framework to deal with arbitrary bias, including the unknown bias. Prior work have proposed to debias with product of experts, POE for short. So let's take text classification as an example. The input feature is X, and the predicted label is C. So there are biasing features XB and unbiasing features X minus B. So with a model directly trained on X, we can get an ensemble prediction based on all features. Since the biasing and unbiasing features are not distinguishable, we cannot directly train a model on the unbiasing features. However, following Bayes' rule, we have the following equations, and we can find that we can get a biased prediction and the mean prediction if we apply the Bayes' rule. So the mean prediction can be computed based on the ensemble prediction and the biased prediction. And the biasing features are typically more easier to collect. So for example, if you already know what the bias is, we can always create such a data set where all instances have the target bias. And even if we do not know the cause of the bias, we can still use a weak model as a biased model, as previous works have found that weak models always captures shortcuts easily. So in the context of large language models, we can use the bottom layers of the model as a biased model, since it has been shown that bottom layers of large language models often capture simple features that can easily trigger biases. So during training, we compute the cross-entropy loss between the ensemble prediction and the goal label, and also between the biased prediction and the goal label. While during inference, we will compute the mean prediction directly. So the problem is that this method relies on debiasing signals which are too sparse. So it relies on the signals being propagated in a top-down manner from the logins to the model parameters. So this will only provide limited debiasing signals to low-level features. And also, although our goal is to mitigate the influence of the biasing features, this kind of methods still use shared features for the biased model and the mean model in the bottom layers. So to address these problems, we look into each layer of a language model. So we found that in a transformer layer, attention is the main media for feature interaction and aggregation. So the output representation of each token is a weighted average of all token representations with attention as weights. So we argue that appropriate attention plays a critical role in ensuring robust prediction. And biased models captures spurious shortcuts through biased attention. So in addition to POE on predictions, we further debias through learning attention residual. In each bottom layer that's shared by the biased model and the main model, we compute biased attention and main attention independently. The ensemble attention is a weighted average of the biased and the main attention. During training, our method adopts ensemble attention to compute ensemble prediction and biased attention to compute biased prediction. So this allows to mitigate biases from the main attention by learning their residual. And during inference, our model adopts the main attention, which is free of bias, to compute the robust main prediction. We evaluate our method on multiple tasks with different biases. The first one is natural language inference with lexical overlap bias, and the second one is fact verification with a hypothesis-only bias. So we can see that the original model performs pretty well on the in-distribution data set with target bias. However, if we test the model on an out-of-distribution data set, the performance is much worse. We can see that the performance, both of the performance drops from about 80, around 80 to 60. So this indicates that the good performance on the in-distribution data sets mainly because of the spurious shortcuts. And previous works have tried to mitigate biases with or without knowing the cause of the bias. And POE is also an effective way to mitigate unknown bias. While our method enhances POE with attention residual debiasing, we can see that our method improves the accuracy by 4 to 5 points. Next, we studied the attention patterns of the vanilla model and our debiased model. So for paraphrase identification with lexical overlap bias, we can see that our model, our method increases the model attention on non-overlapping tokens to reduce the lexical overlap bias. So the left part is a case study, while the red part is the attention on the whole data set. I'd also like to mention that we have a follow-up work in this direction. We apply products of experts on backdoor defense. We propose denoised products of experts and ensemble-based end-to-end defense method for mitigating invisible and diverse backdoor triggers. Here are the takeaways from the second section. So language models suffer from various spurious shortcuts, such as lexical overlap bias and hypothesis-only bias. And mitigating these biases without knowing the cause of bias beforehand is feasible. For example, we can assume that some weak models can serve as a biased model. And appropriate attention plays a critical role in ensuring robust prediction. Based on this observation, we propose attention residual learning. Yeah, any question about this part?
Oh, yeah, sure. I have a couple of questions. This was very, very interesting, I thought. But I wonder, like a lot of people have quite large trained models, and they've sunk some cost into this. Is it possible to apply read as an adapter or some kind of bias correction post hoc?
No, that's a very good question. I think the key point is how to calibrate the attention weights without training. I think these adapters it won't be difficult. We can just apply the same thing like with a PFT model. But for inference only, I think the most important thing is to ensure that the attention residual is calibrated, is aligned to the target model. Yeah, so there could be some challenges in that part.
Yeah, I can see that. Okay, and then also you put up one slide, I think just back one slide perhaps, which sounded very interesting about the backdoors. Yeah. And maybe this work isn't published yet, I don't know, but this sounded extremely interesting. Is there anything more you can say about this?
Oh yeah, so it's a preprint, like already on the archive.
Oh, okay.
So it's like we know that for so for malicious data providers, so they may inject some backdoor triggers to the data set, like for example, shown as a CF or non-cross concurrent or a sentence structure. So they may trigger, they may make sure that such backdoor triggers will be associated with some backdoor behaviors. So that is a kind of risk during model training. So if we use a data set with such backdoors, then our model will have such backdoors that we do not know. So our work focuses on mitigating arbitrary backdoor triggers, defense arbitrary backdoor attacks, even without knowing what the trigger is, and also we also focus on a mix of backdoor setting where there could be different backdoors in the same data set, so it will be more challenging to defend. So we found that we can apply PoE to defend such attacks. So it's similar to the debiasing paradigm. The only difference is that for backdoors, these triggers could be linked to some incorrect labels so that we should further denoise after in addition to PoE. So the whole framework is shown in the red part. Similarly, we have a trigger-only model and a robust model, and we learn their residual to get a prediction free of backdoor.
That's really nice. It makes a ton of sense. I think that's a very creative application of bias correction, right? I mean, backdoors one would anticipate that backdoors have this kind of representation and behavior, so one can correct with them in a similar way.
Yeah.
Nice.
Thank you. Okay, so I have a few more slides about future directions. So for future directions, we seek to ensure responsible use of language models in critical areas, such as medical, educational, and financial fields. So this consists of three sub-directions. First, accountability, including robustness and contextual faithfulness I introduced today. And second, controllability. So the language model should be able to follow natural language instructions and constraints to fulfill human intents. And third, privacy and security. So the language model should effectively defend backdoor attacks and protect sensitive user data. I'll provide more details on each of them. So in addition to robustness and faithfulness, accountable reasoning with rationale has garnered more and more attention recently. So this line of work requires language model to generate explanation or reference to support the answer. We can also improve the reliability of reasoning chains via past searching using symbolic reasoning tools and correcting errors with external knowledge. Controllability is also crucial for responsible usage. While large language models can generate adequate responses to general task instructions, they face challenges when it comes to following more complex instructions with detailed requirements. Integrating various logical constraints into large language models is also non-trivial. And also, users may desire control over the prompt adherence level for flexible text generation, especially for customized usage. And additionally, there's a growing demand for personalized language models. When applying large language models to creative areas, privacy and security issues are also of importance. So this slide shows some of our recent work, recent preprint on jailbreaking, backdoor defense, and also backdoor and also fingerprinting. So we know that the model, a reliable language model should not generate harmful responses, and there should be no backdoor in service providers and sensitive users will expect their private model or data to be protected. Here are my great collaborators. I'd like to thank them for without them, like the papers I introduced today wouldn't have been possible. And before the end, I'd like to mention that we will be presenting a tutorial at MLP 24 on the topic of enhancing language model capabilities beyond scaling up. So welcome to join us if you are interested in this topic. Thank you.
Fantastic. Thank you very much.
Yeah.
Nice. I'm sure there'll be a couple of questions. I guess I definitely have some more that I could ask. But this was all really exciting stuff. Thank you for the broad tour of impressive projects. I wonder so we were talking in one of the earlier parts about using about contextual faithfulness, right? I did a lot of work in temporal information retrieval and temporal question answering. I think time is a non-trivial context to model. And this is also unsurprisingly the case with LLMs. I wonder, so what do you think about having models express old knowledge with an appropriate level of certainty, right? So there are many things in text saying the US president is X for many entities X, right, written over time. But if we have maybe a question of the year is 2040, who is the US president? How could a model? I mean, I would expect maybe quite bad results from a model. I don't know. How could we get reasonable results, do you think?
Oh, good question. Yeah, I think if we can let the language model to provide some evidence like of its answer, or we can let the model to provide some like a certain level of its own answer, then definitely we can let the language model, for example, use to revise its own answers based on these uncertain levels or these evidences it provided. So it would be an interesting like extension to enhance the model faithfulness. Like we prompt the language model to provide more details. It could be some like timestamp, it could be some rationales about its answers. And then we can let another itself or another model to verify its answer based on these rationales or timestamps. So, or let the model to revise its own answers. Yeah, it could be like, it could enhance the language model's faithfulness, but it's not like enhance the faithfulness in the model by updating its parameters, but from a more reliable system, like we have a process to ensure that the answer is faithful.
Yeah, I think there are probably two ways to realize what Leon was asking, right? One way is because the question is, let's say your language model has been updated, but what if we just want to ask about something in the past, which is not the newest, right? Or which is something very, very old, but that's still correct. So I think so one way is that if reg is allowed, then this is basically you do retrieval plus your technique that is presented here, right? You first need to retrieve the knowledge, the old knowledge that is described in some way from somewhere, then make sure the language model is faithful to that, although that is probably already conflict to the current status of the parametric knowledge, right? That's one way. The other way is probably if you don't think about reg, but you want every time-sensitive knowledge to be well captured in training times, and maybe that's actually you may want to actually leverage a backdoor. So the backdoor trigger is actually time, something like that.
Mm-hmm.
Right.
Yeah, I agree with you.
That's interesting. Yeah, I mean, there's a lot of work on modeling things like event duration, right? So one can express certainty after an event of the given type is finished, but modeling them as backdoors, I didn't hear about before. But I think, I mean, if one wants to do bias correction, then the bias correction mechanism for a contextual bias is, yeah, maybe that's worth a try. Interesting. It's very nice to see someone addressing this kind of contextual faithfulness. I think it's a difficult and very important area.
Okay.
Okay, any more questions for Faye?
Hi, can you hear me?
Oh, hey, yes.
Hey, Eric Hacker here. So I was thinking about looking at the sort of adversarial prompts that we've seen, especially that paper that was searching for and finding adversarial prompts. And it's like you don't even need to hide something in the training data. There's already plenty of stuff out there that can lead to problems. And it seems like maintaining some context could remove some of the bias that those are adding into the equation there. Is that something that makes sense as where you're going from a security perspective?
Oh yeah, so it's like, yeah, you're right. Like there are, even if there is no like malicious data provided, the language model may still have some unexpected behaviors triggered by some adversarial prompts. So I think the point is that, like, first, how can we make sure that the language model is like free is robust against these adversarial prompts, like we can do during training, and also during inference, there could be something like defensive strategies that to make to like first we can identify these adversarial prompts, and secondly, if there any like jailbreaking defense or backdoor defense method that will also work on defending these adversarial prompts. So I think the principles behind these attacks are the same. Like there are some triggers and may trigger some adversarial behaviors, unexpected behaviors. So no matter it is a kind of bias, a kind of backdoor, or a kind of any other attacks. So if we can detect the triggers or and defense the triggers, then we can ensure that the model is reliable, is safe.
Sure, great, thank you.
Yeah, thank you.
Thank you. Okay, I guess we have time for one last question, maybe. Or maybe we've given Faye enough of a grilling with detailed technical examinations. Maybe. All right, I'll stop the recording there. Faye, thank you so much. This was really interesting. Really appreciate it.